Hello everyone. Okay, welcome to the screencast for Alkenes. So sorry I didn't make it for class today because I was down with fever and cough. Okay, so can't really speak very loud, so I'll just try to put the mic closer to my mouth. Okay, so this is about alkenes. Just a short recall that hydrocarbons are made of hydrogen and carbon atoms only. We've covered alkanes, so today we'll talk about alkenes. We say that, oh, sorry, this one should be alkenes. Okay, alkenes are unsaturated hydrocarbons, which means that they contain at least one double bond between the carbon atoms and are only made of hydrogen and carbon. So the front part, unsaturated, refers to the double bond, and hydrocarbon is part of the second part of the definition. Okay. So why do we say that it's unsaturated? When we say saturated, kind of means like saturated with hydrogen atoms, so as many as possible. But when there's double bond, there are a few. There will be carbon that there will be less hydrogen bonded to the compound when there's a CC double bond. Okay, so can you try filling in the table with the first three members of the alkene homologous series, and just based on the series that you've written, what do you think is the general formula for alkenes? Try and derive CNH something yourself. Okay, so here's the first three member of the alkenes. We have propene, ethene, we have ethene, propene, then butene. Note that there's no methane because for there to be a CC double bond, we need at least two carbon. Okay, so you can fill in this table. I think if I remember correctly, I did not include the last two. Actually, you don't need to know, like, you don't need to memorize this table. All you need to know is like the general trend. Okay, so can you try calculating the relative molecular mass as well as the state? Okay, so just for information, Hep is up to 7, Oct is up to 8. Do you know what is 9? 9 is actually non. And strangely, 10 is DEC. It always confused me because October is the 10th month and December is the 12th month. So I'm also not sure why they name it like that. But oh well. Okay, so check your answer. This alkene. I just copied this slide from the alkane slide. Okay. But you can see that I got draw the double bond lah. So as molecular size increases, it should show a same trend as alkanes, which means that as the size increase, melting and boiling point should increase for the same reason as in alkanes. Okay, which means that as the size increases, larger surface area, stronger van der Waals between the molecules. So we need more energy to overcome the van der Waals forces, and hence higher melting and boiling point. Okay, flammability it also decreases as the molecular size increases. So what is the difference between alkenes and alkanes? The melting and boiling point of alkenes are similar to alkanes but slightly lower. Why is this so? Now remember that there are two factors affecting van der Waals force, the strength of van der Waals forces. It is dependent on 1. Surface area, actually more of the size of the electron cloud. Surface area actually refers to the size of electron cloud. The second factor is electron density. Now why do I say that each alkene molecule has 2 fewer electrons than the alkane with the same number of carbon atoms? Okay, let's compare ethane. as well as ethene. Okay, let's calculate how many electrons each of these molecules will possess. Remember that one line represents 2 electrons. So for the ethane molecule, I have 1, 2, 3, 4, 5, 6, 7. 7 bonding electrons. So that's 14. 7 pairs of bonding electrons, so that's 14 electrons. On the right hand side, ethene, I have 1, 2, 3, 4, 5, 6. 6 times 2, so that's 12 electrons. So you see that there is always 2 less electron. This is because of the double bond, making it unable to bond to 2 more hydrogen atoms. So therefore they will have fewer electrons. Therefore, van der Waals forces become weaker comparing alkane and alkene. So on the production of alkenes is actually using cracking. Now cracking is a process that involves the cleavage of alkanes by heat. So you just heat up a long chain alkane. In this process, a long chain hydrocarbon from petroleum, you remember petroleum, is broken down into short chain hydrocarbons. You can get smaller alkane molecules, and sometimes hydrogen molecules. So this is the condition for cracking, which you need to memorize. 600 degrees Celsius, silica and aluminum oxide as a catalyst. So what is the purpose of cracking? It is to make 3 things: petrol, which has the function of being the fuel; hydrogen, which has the function to be a fuel as well as the raw material for making ammonia. Lastly, we want to get short chain alkenes as starting materials for us to make ethanol as well as plastics. So there are a few possible reactions. For instance, I can have a long chain alkane becoming a short chain alkane and an alkene. Okay, so for example, let's say the long chain alkane is a C9. Okay, if you see 9, how many hydrogens should there be? CnH2n plus 2. So I should get 18 plus 2, 20. Now it is possible for it to break into 2, such as let's say C4H10 plus C5H10. Okay, remember that the general formula for alkene is CnH2n. Now, you should see that, let me change the color. You should see that the number of carbon should add up. Okay, 4 plus 5 equals to 9. And the hydrogen should also add up. Okay, so we have another possibility, which is the long chain alkane can give us 2 alkane molecule and hydrogen. Using the same example of C9H20, it is possible for me to get, let's say, C3, let me just choose a different number, C3H6 plus, remember that the carbon must add up to 9, so C6H12 plus H2. Okay, note that when I add up all the hydrogen, 6 plus 12, 18 plus 2, it should give me back 20. Okay, so it's actually quite simple, you just need to heat it up. But again, you are unable to control exactly what is the length and what is the exact product that you get. Now, we move on to what are some chemical properties of alkenes. Why do I have so much typo? Alkenes. So there are a lot more reactions for alkenes as compared to alkanes. So alkenes have 2 main types of reaction: combustion, which is the same as alkanes, as well as addition reactions. And you see that there's a lot of types of addition reactions. Okay, so this part, we have talked about it before, for alkanes. Complete combustion is where carbon dioxide and water are the only product. Let's just do an example. For example, C4H8 into E. Plus oxygen will give us carbon dioxide and water. So let's try and balance this equation. There should be 4 carbon and 4 water. That will give us 4 times 8, 12, 6 oxygen. Or it is also possible for there to be incomplete combustion. Okay, let's say C4H8 again, plus oxygen. When the supply is poor, I will get carbon monoxide plus water. Okay, again there should be 4 here, then water, there should be 4 also. But you will notice that the amount of oxygen that I use in this case will be lesser. 4, 4, 4. Okay, then I'll just give you one example lah. Okay, now we move on to the highlight, which is that alkenes generally take part in addition reactions. Why are they more reactive? It's because there are more electron density at the CC double bond. Now, as you know, actually in chemistry, right, all the chemical reaction involves electrons somehow, like in electrochem, redox, it all involves the moving of electrons. So, having greater electron density at the CC double bond makes it more reactive. What is an addition reaction? It is when another reactant is added across the double bond to become single bond. Okay, you can think of it as addition reactions are A plus B will give you C, one product. Okay, let's take a look at some example. For example, hydrogenation. Based on the name, you should know that it's the addition of hydrogen across the CC double bond. So, when we add hydrogen across the alkene, we get an alkane molecule. For instance, C3H6 plus hydrogen, that will give me C3H8. So from propene to alkene. Now, this is actually used in the manufacture of margarine by the hydrogenation of unsaturated vegetable oils. So actually your vegetable oils are polyunsaturated alkenes. And this hydrogenation process is actually not 100% in the sense that it will not reduce all the double bonds. Okay, we'll talk more about this under the application of alkenes. Next, we have hydration, which is the addition of steam across the CC double bond. Okay, maybe I draw it out, it will be clearer to you. For instance, let's draw a propene molecule again. Steam is H2O. What I will get is actually C. I'm just filling in the hydrogen that were originally there. Then I'm adding in the water molecule. How water will add across the bond is like this. Okay, so you add across the double bond. Now you may be wondering, then wouldn't there be more than one type of product? In the sense that, can I have another product like this? Okay, so of these two, which is the correct product? Now, this is something to predict this, which of these two is the correct product. It involves something known as the Markovnikov rule, which is not in your syllabus. So, if you draw any of these two, it will be correct. Okay, take note of the condition. This is something you need to memorize. Same for halogenation. So actually, addition reaction for alkenes just involve putting things across the double bond. Okay, I cannot move to the next slide. Okay. Next we have halogenation, which is the addition of halogens across the CC double bond. For instance, let's use propene again. Never mind. Plus, let's say the halogen is bromine. In the inert solvent, for example, this is tetrachloromethane. We will get a disubstituted alkyl halide, which is like this. You can see that again, we are adding it across the double bond. In this case, there are only one product because only one thing. We only have the bromine to add across the double bond. So, yeah, that's it. You must remember that for this to happen, we must use an inert solvent like tetrachloromethane instead of water. Why is that so? Okay, if we use aqueous bromine instead, we may get two possible products. This is because water becomes able to interact with the reaction as well. What do I mean? Okay, I've given an example here, ethene. So, plus aqueous bromine. So, what they mean is, in the solution, there will be bromine molecule. There will also be water molecule. Now, how this works is, actually, remember how electrons can move? Okay, so remember that your CC double bond here, okay, you don't need to know the mechanism, just for your information. So remember that this CC double bond here is rich in electron. Okay, there's a lot of electron concentrated around there. So what happens is, if the bromine molecule goes near enough to meet it, the electron will move towards one bromine and it will be like this. And what we'll get in the intermediate is like this with a Br minus. Now if you think that there's a Br minus, there's a C plus, just join together lah. Yeah, if they just join together like that, we'll get a bromoethane, dibromoethane. Okay, but water, remember water is a polar molecule, so this is slightly negative. So oxygen from the water molecule, since water is the solvent, is present in huge amount, so it's more likely that this intermediate will meet a water molecule. So what will happen if they meet a water molecule is that you'll get this you'll notice that this oxygen has too many bonds, which is not possible. So it will lose one hydrogen to give us the alcohol group instead. Okay, again, you do not need to know clearly, you do not need to know how this mechanism works. What you do need to know, however, is that just erase this, is that it is possible for you to get two products from this reaction, which is it is possible for them, the addition across the double bond, to be both bromine, or it could be one bromine and one alcohol group. Okay? So, in general, if you want it to be dibromoethane, you must use pure bromine in a inert solvent. What's wrong with mine? Okay. Now think, what do you think you'll observe when you add alkenes to a bromine solution? How do you think that's different from what you observe in a reaction between alkanes and bromine? Think back to the reactions that you see for alkanes. What are the reactions for alkanes and how can it involve bromine? What are the conditions necessary and how is it different from the alkenes? Okay, so here's a video to show you what is the difference when we add bromine to hydrocarbons. This is the video section. Okay, you're watching a video, playing a video. So on the left hand side we have alkanes, on the right hand side we have an alkene. You can see that when we are adding the reddish brown bromine solution, you can see that there's not much change to the alkane. Okay, it just darkens the solution, which means that the bromine did not react. Okay, now next, what should happen when you put it in alkene? You see that the color, the bromine color, instantly decolorizes. Okay, it became colorless immediately. So what does this mean? It means that your bromine molecules have been reacted away due to the CC double bond. You see the end? Oh, yeah, I did. Okay, so what should you observe when we add alkene to bromine solution? Now, this is an important observation that you need to note down, that the bromine solution is reddish brown. It decolorizes rapidly to give a colorless oil. So, this is very important. Why? Because this is the identifying test for alkenes, which means that there are no other functional group that will react in this same way. Okay, so whenever you see that, when bromine is added, the reddish brown bromine decolorizes rapidly, it means that there's an alkene functional group within the compound. Okay, so how do you think it's different from what you observe in a reaction between alkane and bromine? Note that it is possible for alkenes to react with bromine as free radical substitution, but we need it in the presence of sunlight or UV light. Sunlight contains UV light. In the absence of UV light, there should be no decoloration as shown in the video. Next, we'll talk about hydrogenation, which is the addition of hydrogen halides across the CC double bond. So, what do we mean? For instance, let's use ethene. Okay, let's use ethene. If I add HCl, for instance, at room temperature, this will give me a monosubstituted alkyl halide. Okay, note that it's just at room temperature, so we do not need to have any special conditions. Next, addition polymerization is actually a very interesting reaction. It is the process where one molecule, a monomer, we call it, is directly added to another without any loss of any portion of the monomer to form very large molecules. Now, what do I mean? For instance, let's say I have few alkene molecules, what will happen is, note that they have this electron density here, right? So what can happen is, one electron can come here, one electron can go there to form a bond between the two of them. Okay, then this other electron can donate to another molecule that's next to it. Let's say there's another one. Then we can form something like this. See? Now it's a single bond because one pair of electron has shifted away. Okay? One electron move to the right hand side, one electron move to the left hand side. So note that these two electrons will combine together to form one single bond between the two carbons. And if you think about it happening for a huge chain of ethene molecules, you can see that this will keep continuing. Okay, to form a very large molecule. See that there's no loss of any portion of the monomer. Nothing is lost in this reaction. Again, if A plus B gives you C. Okay, so here are some of the common polymers that we see around our everyday life. We have polyethylene, which is the one that I just drew. Okay, the monomer is an ethene molecule, and the polymer is actually fully saturated. You can see that, just like the previous one, you can see that all the carbons form 4 bonds, and they are all single bonds. Polyethylene is actually used very commonly in our household items like plastic bag, food boxes. Polypropylene is also very common. PVC, I think you've heard of it before, polychloroethene. So why is it called polychloroethene? Because there's one chlorine atom here. It's more rigid than polyethylene and is used to make pipes. I think you have heard of PVC pipes before. Now, here's some general knowledge. Have you seen this symbol before? Okay, all the symbols actually tell you the type of polymer that is present. So for example, PP, this is polypropylene. Okay, so how do I usually draw the monomers? I think it's always easier to show the CC double bond. Then if it's polypropylene, propene will be a CH3 here, then hydrogens at the two sides. So I know that when it's a polymer, what I'll do is I just need to remove one of the double bond and join it to the next molecule, like this. Okay, so you can see that they will be joined like this. So that's polypropylene. V is actually your polyethylene. V means vinyl. Okay, don't really know why. P is polystyrene. Low density polyethylene and high density polyethylene. Okay, now your job, PETE is a more complicated formula, so I will not go through it, but this is the kind that's commonly used to make like your ice mountain water bottle and all that. Then actually, if you take away food from our canteen stores, you will notice that you will see these numbers at the bottom of the food container. So next time, just keep a lookout as to what type of number do you get. Okay, this actually helps the recycling center in sorting out the plastics. Note that number 1 is not good because it is not good for many time usage because they found that it actually promotes bacterial growth. So when I was young in primary school, I always use Ice Mountain water bottle as my actual water bottle. So I use it for like months, which is actually not very healthy. Like now that I learned about it. Okay. Okay. So next lesson, I'll talk more about alkenes and the types of fats. Thank you.